Welcome, everyone. My name is Christopher Kuhn. I am a PhD candidate from the BMW Group and the Technical University of Munich from the Chair of Media Technology. And today I'd like to present our latest research results, which we published in our paper, Trajectory-Based Failure Prediction for Autonomous Driving. So what's the motivation of our work? In autonomous driving, challenging situations like complex or novel traffic that causes the autonomous system to require human assistance is currently inevitable. Now, instead of only reacting to situations where a human driver has to take over, it's desirable to predict such disengagements or failures as early as possible. An idea to do this is to use recorded disengagement data from the past in order to train a failure prediction model that learns to predict future failures as well, by basically learning patterns from previous disengagements to then in a new situation detect a new failure. And in this work, we propose a novel source of information about the future, namely the planned trajectories of the car. And then we propose to learn from planned trajectory sequences that have led to both failure and to success in driving, and then train a model that classifies the current situation basically as failure or success in order to predict disengagements. So how has this been done before in the literature? One group of works is to use disagreements to predict failures. Those papers commonly use an end-to-end steering angle prediction network as a proxy for an autonomous car, since real road autonomous systems are hard to come by. And then they use the disagreements of this end-to-end network with, for example, in this work, the Tesla autopilot. And then based on a disagreement threshold, they can infer impending disengagements 5 seconds in advance. Another work predicts disagreements with the angle output by a human driver based on visual input, so camera images, and also the state of the car, and they achieve accurate results 2 seconds in advance. We follow a slightly different approach, which is to use the idea of introspection, which was first introduced in the context of predicting crashes of a drone that used videos from previous crashes to then learn patterns that indicate basically such a failure. And this idea was used by our group last year to achieve state-of-the-art failure prediction performance in autonomous driving, where we used state data sequences from previous disengagements in order to learn patterns that allowed us to predict new failures 7 seconds in advance. And in this work, we follow this line of thinking, but propose this new idea of using trajectories as input data. So how can we motivate this a bit more clearly? Now here you can see the planned trajectories of 10-second sequences. So each color corresponds to 1 second. And we have both successful sequences where nothing really happens in those 10 seconds. And we have failure sequences where at the very end, the car disengages and the human driver has to take control to ensure safety. We can see that in the undisrupted driving, the planned trajectories are mostly exactly what the car drives. So it's mostly one consistent line and the trajectories don't diverge at all. However, in the failure sequences, we see that pretty early in those 10 seconds, the trajectories actually start diverging. So the car does not drive the planned trajectory, but instead diverges from it. For example, here you can see a planned left turn of the car in the lower right corner, which the car, due to complex traffic, is not able to make. So after several attempts, eventually the car assists human intervention to safely perform this left turn. And this actually was basically noticeable just in those 10 trajectories pretty early when the trajectory started diverging. And we propose to use those trajectories as input for a machine learning model that then learns to predict these patterns as early as possible. So how specifically do we propose to do this? Instead of learning directly from the whole 10 seconds, we split those 10 seconds that consist of a total of 100 trajectories, so 10 per second, into shorter samples. Meaning we split them up into 3-second samples that largely overlap, resulting in a total of 71 samples per 10-second sequence. And each of those 3-second samples that consists of 30 consecutive trajectories Those we use as input to train a long short-term memory network that then classifies each sample as success or failure, depending on whether this 10-second sequence was part of undisrupted driving or led to a disengagement. The proposed architecture is very straightforward. We use a few LSTM layers, followed by fully connected layers, and finally a softmax layer that performs the actual classification. Now that we have a model design, the next question is, of course, what data do we use to train it? Here, we collaborated with the BMW group to obtain data recorded on public roads by their automated development vehicles. From several months of recording, we extracted all disengagements, a total of 2,600 events, where either the car required assistance or the human safety driver intervened by themselves. And we also sample an equal number of undisrupted sequences from the much larger part of recordings where the car drove successfully. And this way we obtained a balanced data set. Each sequence is 10 seconds long. We use a frequency of 10 Hertz, meaning we use 10 planned trajectories per second. Each planned trajectory consists of the next 30 points, which are time fixed. So basically the next 30 time intervals that the car intends to drive. Okay, so then we experimentally validated our proposed approach by first selecting a few baseline methods. Of course, we compare it to the state of the art. Here we used the approach from last year, where state-of-the-art failure prediction performance was achieved using state data sequences, so sequences of the speed, the angle, the acceleration, and so on. And then we also use two baselines where we investigate whether it's necessary to directly learn from the trajectories or whether we can handcraft manual features to predict failures. And this is inspired by the fact that looking, for example, at the degree of curvature of the trajectories, we see that failure trajectories contain much more turns and maneuvers than successful sequences. And also the length of the planned trajectories decreases when a disengagement is approached, which is due to the car usually braking when approaching a novel or complex situation. So maybe it's enough to also just use these handcrafted features to already distinguish between success and failure. To evaluate this, we performed an ROC curve analysis. And to the left, you can see the comparison of the proposed trajectory LSTM approach to using handcrafted features of the degree of curvature and the length, where we trained both a support vector machine and a slightly more complex LSTM using the proposed model architecture. And we can see that that learning the features instead of using handcrafted features outperforms the handcrafted features by 10%, indicating that the proposed LSTM approach is the most promising direction. When we compare to the state data approach, the new approach outperforms it by 3%, again indicating that trajectories are a more promising source of information about the future than only the current state, which of course only reflects the current situation. And finally, we observed that a combination of state and trajectory data actually performs even slightly better, which indicates that a combination of all information available about the current scene is the best way to go for predicting failures. And this combination was simply done by averaging the predicted failure probabilities from both models. Finally, we evaluate the proposed approach by looking at the most interesting quality, which is how well can it predict failures in advance. So now we look at the error over time. Here we have both the success sequences and the failure sequences. We always first need to observe 3 seconds before we make our first prediction, so only 7 seconds are shown. And here we see that in the success case, the prediction performance is mostly constant since nothing eventful happens. And we see that the trajectory approach consistently outperforms the state approach, and again, the combination performs best. In the failure case, it's interesting to note that right before the disengagement, the state and trajectory approaches perform almost the same, which is largely due to the state already reflecting all the changes that could have been seen in the trajectories. So right before the disengagement, the state of the car has, of course, already changed a lot as well. However, 7 seconds in advance, we see that the trajectory-based approach outperforms the state approach by 6%. And this is exactly the motivation of this work. The trajectories offer information about the future, whereas the planned future from the point of view from the car, basically, whereas the state data only shows the current situation, which eventually reflects those slightly more diverging trajectories that the car has planned all along. So this really highlights the strength of the proposed approach, that it offers an improved failure performance many seconds in advance. Okay, to conclude, we observed that the failure prediction performance significantly improved when using the planned trajectories as a novel source of information about when a disengagement will happen. We used this to outperform the state-based state-of-the-art approach by 3%, or 7 seconds in advance, it even outperformed it by 6%. And this is not just limited to autonomous driving. In fact, it's applicable to any robotic system where planned trajectories are available and we want to predict some sort of fail state. So for example, this would also be applicable to robotic arms, manipulators, or drones, where we have recordings of failures and the planned trajectories led to this failure event. Thanks to the model being very lightweight and the proposed architecture being very compact, we can run this model at less than 6 milliseconds per prediction on an average laptop GPU, meaning we introduce almost no overhead and can easily achieve the required frequency of 10 failure predictions per second. For future work, it would be interesting to combine this black box approach, where we look only at previous failures to then predict new ones, with the current assessment of the system. So for example, internal confidence measures of the scene perception, of the trajectory planning itself, those measures could be combined with the failure prediction based on the patterns observed in the data to optimize the accuracy of the failure prediction. And finally, an interesting direction would be to use our information of an impending failure 7 seconds in advance to actually change our trajectories until we can avoid the disengagement in the first place. So by constantly running our failure prediction, we could then change the trajectories until no more failures predicted, for example, by switching to a different strategy, to a more conservative strategy, which would allow our proposed failure prediction model to then effectively become a failure avoidance method. So this is an interesting direction for future work and highlights the promise that the 7 seconds in advance really has in the field of autonomous systems. This concludes our presentation. Thank you very much for your attention. Here you can find our contact information. So we would love to hear from you. If you have any ideas, comments, feedbacks, don't hesitate to contact us. And thank you again very much for listening.